We have to talk a bit about the way that Python parses strings before we can go any further. So here's a string I'm going to create that has nothing to do with regular expressions. So HELLO, I'm going to write this \n WORLD. You should know by now that if I actually create this string, there is no letter N anywhere in the resulting string. There is no backslash. Because when Python parses this, it turns this subsequence, \n, into a new line character. That's an example of an escape character. Whenever Python sees a string, it applies that automatically. That's fine. That's a great feature to have. The problem is that the backslash is also used for a similar reason by regular expression parsers. So for example, \w is for a word character. \s is for a whitespace character. And if I want to represent a literal backslash, the regular expression parser has to be given this. 2 backslashes. If I want to search for an actual backslash in my string, I have to give it 2 backslashes. But what I mean by give the regular expression parser 2 backslashes is, I mean that the string that goes into the regular expression parser has to contain 2 backslash characters. But you can't easily create that in Python. What if you wrote something like this? Let me clear this. If I wanted to search for 2 backslashes and I write this, this string here, you can try this. This string has length 1. Because when you create the string, Python sees 2 backslashes and says, oh yeah, you want a backslash character. So it gives you a string with 1 backslash, which means if you want a string that actually contains 2 backslashes, you end up with this monstrosity. This is a nightmare. And imagine looking at a regular expression, which is already cryptic, and having to put up with something like this. So there is a workaround, and as a best practice, it's encouraged that we pretty much always use this in Python when we're working with regular expressions. So for example, if I wanted to actually store the characters \n into a string, I would have to write \n. Because if I just put \n, Python would sub in an actual new line, which I don't want. And this means that it and the regular expression parser, which are 2 separate things, could get in each other's way. So Python has this option called raw string parsing, which is a way of, when you enter a string, telling it, do not do any of the normal escape character stuff. So I saw on that previous slide, I had this string here, hello \n world, which Python would parse normally to have a new line in the middle, not a backslash and an n. But if you put the letter R outside of the string at the beginning, you're telling Python, do not do escape character stuff. Just leave it. Give me the string I actually typed in. And if you do that, the string you get will actually contain the characters \n. And because of all the backslashes that regular expressions typically need, it's considered a very good idea to always use raw string parsing when you are entering a regular expression. To always put that lowercase r at the beginning to avoid any unforeseen consequences when the parsing of escape characters, when the string is parsed, gets in the way of the way that the regular expression parser handles it when it receives the string when you call the regular expression functions. Okay, so as an example, here I'm creating 3 strings. If I write with normal syntax s1 equals \n in square brackets and I print it out, notice that what I print out apparently contains a new line. If I write this, \n, well then the string, because Python escapes this to 1 backslash, actually contains the text \n. Well, that's nice. But this is ugly and weird, and regular expressions are going to be ugly and weird enough as it is. Notice that I'm not even using them on this slide. And so if I use raw string parsing, where I put an r at the beginning, and I put the \n as usual with no extra escape character, I get exactly what I want, because Python doesn't do the normal escape character parsing it would do otherwise. So going forward, when I create regular expressions, I'm always going to put them in raw mode. Although you don't have to, because we saw in earlier examples that I didn't, it's considered a best practice to make that a habit, so that there is we don't end up later getting ourselves into trouble and having a debugging nightmare because we forgot that lowercase r. All right, now there's this. Design a regular expression that matches this relatively restricted C variable declaration. Back at the beginning, I showed off a really disgusting looking variable declaration. We're not going to get to that point today, but let's see if we can match the basic C variable declaration, possibly including an array declaration. So a declaration of a multi-dimensional array, 1 dimension, 2 dimensions, 3 dimensions, or a single variable. And for the sake of making the example more readable, let's assume that the base type will always be int. It shouldn't be difficult to adapt this to work with floats or chars or something, but for the sake of keeping the pattern big enough to fit on a slide, we'll just use int. And it's worth, whenever you are given a problem like this, if you weren't given this table, make this table. Make a list of things you know are not supposed to match and a list of things you know are, and then refer back to it. And because it's important that if we misuse a quantifier, like if we use the star in the wrong way, that we could end up accidentally matching a declaration of no variables, or matching a declaration with no name, or matching a declaration where the first character of the variable name is a number, which isn't normally allowed. Normally you can have numbers in a variable name, but only after the first character. So having this table is helpful. It gives us a point of reference. And then what we're going to do is work our way up from basic declarations, which will hopefully give us enough context to avoid some obvious problems. We'll work our way up from there to declaring one array at a time, and then eventually to declaring multiple things in one declaration. So we'll develop this iteratively. Okay, so first, this pattern here matches the word int, then a space, then a letter or underscore, because we know that the first letter of a variable name, or the first character of a variable name must be a letter or underscore. It can't be a number. But after the first letter of a variable name, we can have any alphanumeric character or underscore, so \W. Notice that there's a star there because I have to be careful that I do want to match variables that only have a one-letter name, where this letter is the only letter in their name. And then the pattern ends with a semicolon. Okay, so it matches int x, so that's pretty reassuring. I obviously need that. It doesn't match int x with no semicolon, but that's good. So this is good, this is good. It doesn't match this, and this is obviously valid. There's extra spaces. I should be allowed to put as many spaces as I want between the word int and the letter x, as long as I have at least one space, because if I didn't, then I wouldn't have a valid type name. Int var1 works, so apparently multi-letter names work. An empty declaration doesn't work, so these two are good. But I still need to do something about that number of spaces. So I'm going to work my way up from the beginning. What I have right now, I think, is readable. I think I could start with this. If somebody handed me this pattern, I probably could start there and work out what it does. I will not be able to do that with my finished pattern, so it's important to develop this iteratively. So we know that it seems like it works in general. We have enough test cases to suggest that we're on the right track. We have a problem with spacing. So what I'll try is I will try using, instead of a literal space character, which could cause me problems in case somebody uses a tab, I will begin using \s. And I will start with sort of the obvious foolish solution is \s star. And remember that that star could match 0 times. So this works, this works, this works. So I've solved the immediate problem from the previous slide, but this is now a big deal. Int x without a space between them. Because the s star matches any amount of white space, that includes no white space. And so this is considered to match even though it should not. So the solution here is that I need to make sure that there is at least one space after the word int. So maybe I should change that to a plus. So I have this, s plus. That means that it requires 1, but there may be as many extra after that 1 as could be. So we have that. It's also worth noting that an alternative would be to write something like this. If for some reason you hate the plus operator, you could always use, you could double up, \s followed by a \s star. Because the first \s gives you your 1 space, and the remainder gives you 0 or more supplementary spaces. Now the question is, I guess I can declare one variable, but what about declaring multiple variables, not worrying about arrays just yet, multiple variables in one line? And we can see things have already been amplified quite a bit. This is quite a bit more complicated here. But if you look at it, what I've done to be able to declare multiple variables is I've thought, it sounds to me, based on what I've already seen, based on my existing testing, that this is able to match a single variable name. So I'm confident in this. I've tested this enough in isolation that I'm confident. So I think if I want to match multiple variable names, well, I need to make sure I'm matching at least one variable name. But then what I could do is look for as many other names of this type as could appear by using a quantifier. And so I end up with this. So let's walk through this. I match the word int. I match some spaces, at least one, but as many more as could be there. And then I match a variable name. Okay, and a variable name is defined the same way it was in the previous example. And then I think, okay, what does it mean to have a second or third or fourth variable name there? So I have my first variable name, and if there's going to be a second, third, or fourth one, there will be a comma followed by some space, and we know already that some space, especially when the comma is concerned, could indeed be 0 spaces, but it could also be 100. Followed so that we have some space and then another variable name, and that might repeat. I could then, if I wanted to, I could then have, comma var3. I could have as many extra terms as I want. After the first term, each extra term is a comma, some spaces, and then another name. And then when I'm all done, then I have that semicolon. Then I have that semicolon at the end. So what I've done here is I've thought, well, I want to have as many extra terms as there could be, but I know that after I've seen my first name, there do not have to be any extra terms at all after that. So I'm going to use a star quantifier on this sub-expression. The sub-expression will be a comma, some space, a variable name. And then I put a star on it because I want to allow the possibility that there are 0 extra variables declared in this line. And so I can see this does match all of my examples, although I guess it's worth considering. I am forgetting. I guess I forgot to include an example where I'm declaring 3 variables on one line. There's no such thing as too much testing. And so, yeah, the slides are, yeah. The previous slides didn't talk about the array declarations just because we wanted to get our bearings, and we know that we're going to have to handle cases like this anyway, but now that we've done that, I guess we have to begin talking about array declarations. So let's start with what we already had. So here is, from the previous slide, the example that will match multiple variable names with no array stuff. And it does work, and actually here is our case with 3 variable names, and it looks like that works fine. But it doesn't match these cases where I'm declaring arrays. So int a with square brackets 10 or square brackets 10, square brackets 20. So we'll start from this and see what we have to do to adapt it. And actually, I'm going to back up on that, so I forgot the slides do this. I'm going to back up and say, maybe what we'll do is actually back up to this point. Let's not worry about doing multiples of these. Let's instead see if we can make it match one array declaration and then work from there. The reason really, pragmatically being, because the pattern is going to get so long it won't fit on a slide if I do it that way. And so we'll scale things back and then work on array declarations starting at the more basic case. Okay, so we scaled it back. We're just going to worry about matching one array declaration for the time being. So currently, we've actually managed to break part of our existing pattern because we no longer handle multiple declarations. What I want to do is find some way of matching this square bracket thing. And I want to allow the possibility that there could be extra instances of square brackets, in fact, as many of them as I want, as long as there's at least one of them if I'm declaring an array. So I think, well, what does this actually look like? Well, for now, and I'm cheating a bit here because in real C syntax, the expression you put in here can be anything you want. I could have it be like n+5 or something like that. But suppose that I only care about actual numbers, which was what the prompt said, then what I'm looking for is a square bracket and then at least one digit, but maybe more, and then a closing square bracket. And I should observe that if I ever see an array declaration with none of these square bracket things, well, that actually is still valid. It's just not an array declaration. It's just a declaration of a regular variable. Okay, so I'll start with this. So what I'm doing here is I'm trying to match a declaration of either a regular variable or an array, but only one of them. So I match the variable name like I was doing before. This part is the variable name. And then I have this bracketed optional sub-expression. Notice the star. This thing in here could appear 0 times. And the case where it appears 0 times would be something like this, where I'm just declaring a regular variable. Okay, so what is in the brackets? Well, I want to match a square bracket, but we know that square brackets already have a meaning, so I can't just put a square bracket by itself. I have to use \square bracket. So it's good that I remember that lowercase r. So I use a square bracket, then I match one or more digits, that's \d, and then I match a closing square bracket. And And this term, this array size thing, can appear as many times, including 0, as I want. And so we notice it matches this. It even matches this. I'm already being able to handle 2D arrays, but it doesn't match this. Well, this is correct, actually. It shouldn't, because this shouldn't be here. I shouldn't be allowed to match a case where I've got some random identifier sitting in the brackets. So I'm now able to match one array declaration or one regular variable declaration. So if I rewind a bit, I might observe, once I figured out how to match a single variable declaration, I was able to adapt that to match multiples pretty easily. And I'm going to do the same thing here. So because the pattern would barely fit in the slide, otherwise I've stored it in a global variable here to move it over to the left. So what I'm doing here is I am matching the word int, some spaces, and then one variable declaration. That's one complete variable declaration, variable name, possibly some square brackets, and then as many other ones as might appear. And notice I actually have nested brackets. I actually have a sub-expression inside a sub-expression here. Of course, that's no big deal. We know already we can definitely nest brackets in lots of other settings too, in lots of programming languages. And so the pattern I end up with, I'm sure, if you handed this to me, I would say, what the hell is that? I've got no idea what to do with this. But notice that if we just walked through it step by step, we were able to, reasonably make improvements over time that made it work. It's just hard to go all the way backwards because of how cryptic it ends up looking. And so regular expressions are often actually called a write-only language for that reason. They're far easier to write in most cases than they are to read.